Thank you. I realized when putting together this, we're going to talk about Internet of Things devices today, and I realized that this title was a little bit kind of misleading, that functional Internet of Things kind of sounds like we're talking about making not broken Internet of Things, but the reality is using functional programming languages. So that doesn't roll off your tongue as easily as just talking about functional or IoT. So to set things up right, a lot of people are curious these days when it comes to embedded systems and whether or not you can really apply that term loosely to these machines that we have that are available to us. Because they can run Linux, people usually tend to say that's not an embedded system. But the reality is, for the sake of these talks, that if you have a tiny computer and let's say you attach a sensor of sorts, in this case this is a moisture sensor, and then that tiny computer uses that information to actuate some sort of thing, then if we put those things together, voila, single purpose computer, that is an embedded system. Now, if we take that one step further, we'll see that if you take this embedded system and you attach the ominous cloud to it, voila, that is IoT. Pretty simple and straightforward, but usually like to just get things set up front there. All right, so as mentioned, yes, my name is Justin Schneck. I started my career out in embedded systems with an idea. I wanted to be able to remote start my motorcycle from my phone. And after a lot of staring at schematics for my motorcycle, I had a Triumph for long periods of time, I finally worked up the courage enough to be able to cut into the wiring harness and essentially figure out how to put all the pieces together. I went further into that. I made an embedded wearable system into a jacket to be able to experiment with cross-communication, as you can see in this image. And then one step further, where I actually ended up just pausing for a minute, was when I decided that I was going to communicate with the onboard computer and detect lean angles and then start messing with the timing of the engine. After learning my mistakes from flying drones, I decided that might incur a little bit too much pain for my comfort. So I led it up to this level. But essentially, the outcome of this is what drove what we're about to see, the product of this talk. Because the reality is that, and by the way, this was about 9 years ago when I created this device. The reality during that time, as I found, was hardware is hard. And I don't know why I thought this would be any different. I mean, it's right there in the name. It's hard. So the idea is that when you put it together and you create individual devices that can do these things, it seems pretty simple. But the difficult bits come into play when it involves connecting it all together and maybe wiring it up to the sky so that you can have all of this information available to you on your phone, tablet, computer, whatever. Linking all of that is the tough space. Getting the individual pieces working isn't too terribly difficult. So what makes this so hard? Well, one of which, when we see if we zoom in on these components, one of which is reliability. This is a little bit different when we talk about reliability from a hardware perspective, because these devices are usually placed in the field, and it's pretty difficult to be able to get to, especially if you're creating an end consumer product. You don't want to be able to say like, oh, I'm sorry you bricked your device. Can we just come over to your house and reflash that for you? They usually have to be isolated machines that are far away. And so making sure that you can always update it and prevent it from becoming a brick is a big step. In addition, the tooling for these kinds of things is quite immature. It's often convoluted with these massive tool chains and like just CLIs are messy, and all of these different components like build tools that you have to understand just to be able to get something to compile so you can put it onto a device to be able to get it consistently run. And furthermore, when we do this kind of stuff, we don't just usually have to deal with one language. I mean, with devices come user interfaces, and with user interfaces usually come different languages. And then on top of that, you need to almost have like a sysadmin mindset, because these are full-fledged computers in a way that are single-purposed, but you still need to be able to understand how to manage them from a top-level perspective so that you can ensure that your program is always running. And then further complications and multi-language problems comes the entire IoT side of this, where we want to connect it up to the cloud. We have to then understand what the server components are like, databasing, message brokers. It's just a massive amount of information. And so to be able to make this easier, if we can strip some of these problems away, then the answer and the solutions that we've found in applying this is with using an ecosystem of sorts in a language, like Elixir. So I want to answer then first, like, well, why Elixir? I mean, it's a newer language, and why not something else that's a higher level? And first, why Elixir, I would say, is the biggest proponent is that it's built on top of the Erlang VM. The Erlang VM is, Erlang and the Erlang VM have been around since the mid-'80s. And the interesting part about Erlang is that it was originally designed to run on telecom switches, embedded hardware. And that embedded hardware needed to have the highest level of reliability so that when you pick up your phone, it doesn't just go like, I'm sorry, we're in the middle of a system update right now. You can't call the person you're trying to call. And with that, then it also needed to be resilient in that it can run in the most harsh environments. And it was designed with concurrency in mind. So Erlang also uses lightweight processes. Everything's a process. And these processes are using this model called the actor model. They, in isolation, allow you to be able to reduce the blast radius of issues that might occur in your code. And it's got immutability, which means that the data, when you set assignments to variables, that those are sort of immutable and that your data is not going to change. In this functional programming mindset, we don't have things where we're going to constantly be changing this like rolling, this like passed around state, like object-oriented styles. We have this immutability features as well. And as I mentioned, concurrency. Concurrency is an interesting one because we've seen these days with machines, they're becoming more powerful by adding more processors. And so when we add more processors, we need ways to be able to leverage those. And in the case of a single unit, Erlang is nice because it knows how to be able to apply schedulers across all of your processors to be able to make them all available to you. And because it uses message passing and isolated lightweight processes, in that fashion, not only does it make it work on single machines with multiple processors, but it allows you to be able to do distributed programming quite easily. So another great feature of Erlang is its fault tolerance story. And so in this picture here, we'll pretend that we have these things called supervisors. Supervisors are the green squares, and the supervisors supervise processes. So when you spin up a process inside of Erlang, you'll have that process supervised. And then in the case of a catastrophic failure, the Erlang way of thinking is to let it crash, because the supervisor will be able to respawn that process in a known good working state. And then that way you're not trying to always pick up the pieces when you have this bad state and try to make sense of it. The idea is just to throw it away. We got into this weird place, respawn our new process into a known good working state, and let the messages come back in through again. This all happens in the background very quickly without skipping a beat. It's wonderful. And if we wrap this all up, another layer, if we step back further, the other idea is that we're reducing the complexity and the way we have to think about these systems by living inside of Erlang, because Erlang also contains system design constructs. So the idea in Erlang is that you'll organize your code dependencies and its dependencies as applications. That's a capital A. It's an actual type in Erlang. And so you'll say, like, I have these applications. These applications will contain their own supervision trees. And that way, everything is still in this level of isolation. And the beautiful part about that is that you don't need to have external forces that you need to understand, like systemd or like strange Unix, Linuxy things that are in your actual like operating system, to be able to ensure that your code continues to run. And if we take one more step back from there, when you're ready to package your Erlang Elixir application up, your bundle, you can make a release. They're called OTP releases. OTP these days seems like a bad term for this, but it was originally stands for the Open Telecom Platform. Made sense at the time, not so much anymore. Yeah, they're known as OTP releases, and that way you can then bundle all your code up and ship it out to a location that you can then use. All right, so another great thing about Erlang and Elixir, Elixir especially in this case, is the ecosystem. So here's a list of some things that I want to cover today as far as what is available in the Elixir ecosystem. On the top left here, we can see we have something called Nerves Project, which, as I mentioned, I'm the co-author of as well. We're going to talk more about that. Phoenix, which is the web framework for Elixir. Ecto, which allows you to do databasing. Circuits, which is for interacting with lower-level hardware over protocols like I2C and SPI. We'll also talk more about that. Scenic is a user interface library, and Hex for package management. And the nice thing here is that if you're needing to be able to do some specific tasks and somebody else out there may have solved them, then having a step up from C or C++ traditional style embedded programming for microcontrollers and processors, you can bring in dependencies and packages and be able to bring those into your application quite easily. And with this level of with the amount of things that are available to you in the ecosystem, you have an enhanced level of connectivity to be able to allow your devices to connect to the internet and perform higher level tasks as well. So the first thing I want to talk about from the ground up, because we're here to be able to talk about embedded systems as a start, is Nerves Project. Nerves Project is the embedded arm, sort of the Elixir ecosystem. And essentially what it is we take the Erlang VM, and we take embedded Linux, and we smush them together. And then in the end, we output firmware. So the concept with Nerves is that we want you to be comfortable in higher level languages. And so we want you to spend most of your time programming your application and your runtime in Elixir or Erlang. And from within that, because the Erlang VM has all of these system design ideas from the start, the Linux kernel is only sort of there to be able to help us bootstrap a lot of the lower level things. We get a lot from Linux. We get the driver support. So if you plug in like XYZ device, it likely has support in the Linux kernel for it. This allows us to be able to build on these things quickly and allows developers to be able to move faster because they can stay in higher levels. So just like here, this is an idea of how you do web deployments. We're all familiar in the case you can just take Elixir and replace it with whatever your favorite language is. You build a release out of that product and you dump it on your web server. So just like that, the way that Nerves works with Nerves deployments is that you take your Elixir application, it creates this OTP release. That OTP release is then burned into firmware and put onto the device. All right, so once it's on the device, so Nerves has that compile time component of building this, cross-compiling this system, because these are usually other processors than the one that's in your machine. It'll burn to an SD card in this case, and this is an image of what the Nerves runtime would look like. So a Nerves runtime is split into a partition scheme where you have some general boot information up top with some provisioning information, like let's say the device's serial number and some other information. And then we have slots for the root file system. We have a root file system A and a root file system B slot. And at the very bottom there, you can see we have another partition that's laid out that's application data. And the important thing about Nerves runtime here is that primarily we ship with a blue-green deployment style. And this helps with reliability, preventing bricks in the field. Let's say you're booted off of file system A and an update comes in. You'd stream that update to file system B, And then what you can do is you'd switch the master boot record at the last minute, try to boot into file system B. If the boot is successful, then you mark that as the active file system. If it's unsuccessful, then you always have a known good working place to be able to recover back to, and you just fall back to the old version of the firmware. And then at that point, you can try to stream in back over root file system B, a good firmware update, and so on and so on. Ping-ponging back and forth. In the web world, this would be blue-green deployment strategies. The other important thing to mention is that root file system, your root file system inside of the Nerves runtime is read-only. And there's several really good points about this. One, the device power can just kind of like be expected to be pulled at any time. And so if you have a read-write file system and you're writing files to that file system, you're going to corrupt that, and it's highly likely that you're going to cause a brick. To be able to get around the fact that people still need to write state somewhere for persistence and for rolling updates, that's why the application data partition is there. It's a place where we allow you to be able to store your state. And it's also mentioned then in that case that you should have a way to be able to recover that in case a system were to have the power pulled out of it and you corrupt the application data. Also, Nerves systems are a whitelist approach. We only turn on the kernel options and the things that you need. And so they typically ship with everything good to go with your application from a start at 30 megabytes, which allows you to very easily ship and stream them over the air and costly internet connections like cellular data connections too. Nerves runs on a variety of different hardware. First and foremost, every Raspberry Pi made ever. That used to list them all, but it was just silly after a while. And yes, we just support every single Raspberry Pi made ever, which makes rapid prototyping pretty quick and easy. BeagleBone is a less familiar one. That's actually an open hardware spec. And so if you're looking to be able to produce your own hardware, adopting the BeagleBone platform is nice because you can take the chips and components on it and respin them to however your board sees fit. We also support x86 machines. At Latote, we build, we basically take all-in-one machines, which have like ridiculously large hard drives, like 1 terabyte, and put 80 megs worth of data on them, and then boot off of those. And there's a board called GRISP2. GRISP is an interesting another Erlang project that is looking to be able to use real-time operating systems to ship support for embedded systems. But it's also interesting to mention that it will support basically anything that can run embedded Linux. We have advanced guides to be able to take additional boards that you might need and get them working with Nerves. So let's see how quick and easy it is to be able to get up and running with a Nerves project. So the first thing here, once you have Nerves and Elixir and Erlang up and running, you'll find that the tool to be able to work with this stuff is called Mix. So we'll say mix nerves.new. We'll just call it my app. And that'll create a new project, and it'll ask if we want to fetch and install our dependencies. We'll say, yes, sure, do work for me. I like that. And then once it's done creating a project, we'll cd into my app, and the first thing we need to do is determine what target we're booting off of. In my case, right here, I have a Raspberry Pi 3A+. It's a really fun board, and I have a micro SD card. So I'm going to pop my micro SD card in, and I'm going to export my mix target to RPI 3A, because Nerves project is cross-compilable. You do that by setting what target you're working on at the time. And then right away, I'm going to call mix firmware .burn, which will compile my application. While it's compiling here, when it finishes, we'll see that it'll create what we were talking about, an OTP release. Now it built the OTP release, and at this stage, it's taking the root file system, putting the OTP release in it, attaching the Linux system for the Raspberry Pi 3A that we've pre-digested and put in up for use with Nerves project, and then burns it to this firmware file. And now it discovered my SD card, asks me if that's the one I want to use, and after I type in and authenticate, voila, I have an SD card. And I'll pop that into my device and plug it in. So it just takes a second to boot here. Whoop. All right, and to see that we're up and running then, we'll do the unique thing about this board actually is that I have a USB cable here, but over that USB cable, it's doing a virtual serial port and Ethernet connection, so I can just do SSH, nerves.local, and I'll get an IEX prompt for the REPL instead of a bash shell. And we can see that we're attached to our device. That's how quick and easy it is to be able to get up and running with Nerves. All right. So as we can see, what's the debugging story like with this? We got our project bootstrapped, we're ready to go. You can use SSH to be able to connect to your device, in this case over USB. In the case of Raspberry Pi Zeros, it's also USB, but larger devices you can connect using Wi-Fi, Ethernet, all of that kind of stuff SSH will work over. And deployment updates sort of work in the same fashion. Let's say you're going through your code and then you get to the point where you hit a bug and you're like, oh, I really want to be able to update this, blah, blah, blah. You fix it and you're good to go. Then you can, instead of having to burn SD cards every time, we can just push over SSH. So let's just take a look at what that looks like. We'll pretend like I've made some major awesome change here and change my version from 0.1.0 to 0.2.0. And after I mix firmware again, which takes a little time, we'll say we've ran that, we can run this script. So it's, over SSH, we have a little helper script. So we can say mix firmware.gen.script. And then we have this little helper script, and we can say upload.sh. And over my Ethernet, over my virtual Ethernet connection, I've streamed the new device firmware, and the device reboots into the new slot. Since my window is a little small here, that's supposed to do this, in ncurses. But you can see it says upgrading partition B, streaming this UUID firmware, the unique firmware to that device, and after it reboots, we're up and running. All right. So that works great in development, but what happens in production? Devices that are in the field usually aren't available over SSH. You try to push that to the cloud, and that request is just going to get blocked by everybody's firewall. So to answer this problem, from the Nerves perspective, we also went forward to be able to create a project called NervesHub. And now, NervesHub is a web service that your devices will communicate with and allow you to be able to do fleet management for these devices. So in this case, let's say we have these ones here, and we're going to create a deployment group. We're going to go, OK, this group of devices here, that's production. And when I want to upgrade production, I can just say from the command line, mix NervesHub firmware publish. That's going to push that firmware to NervesHub. And then NervesHub's going to deploy update strategy down to those devices for us. Now, because we're responsible developers, we don't just push to production. NervesHub has ways of being able to integrate with your development pipelines. So you can instead create test and QA and production deployment groups. And then from whatever CI tool that you're using, you can say firmware publish it, push it to the test group. You can even do automated testing, capture the results, and then forward those to additional deployment groups to be able to advance that firmware through your company's stages. NervesHub's very secure. We take security really strong in this case because we don't want to. We've all heard, the popular jokes. Oh, the S in IoT is for security. Well, we want that joke to kind of go away because first and foremost, we're focused on this as an effort. NervesHub secures the communication between your terminal, pushing the firmware to the browser using client-side SSL certificates, as well as between NervesHub and your devices. And to go one step further, we're strongly advocating the use of this device that we've created called NervesKey, which is essentially just a cryptography chip on a breakout board. It looks like this, and we actually have them up for sale for little to no, like a price. I believe they're about under $10. And the idea with this is that it solders onto the back of your device. In this case, you can see it attaches to the back of a Raspberry Pi very easily. Or you can put it on a breakout board. Or you can actually order this chip that costs, like less than $1 and embed it onto your device for your product. And what happens is, this is essentially, if you're familiar with the term, an HSM, which is a hardware security module. It means that when you generate private keys, like SSH keys and SSL keys, that the private key never leaves that chip. And all of the authority for that key is then asked to be computed on the chip. And this way, everything's more secure. The keys that we generate on these chips are also compatible with not only NervesHub, but other services such as Amazon's IoT and Microsoft Azure IoT services and more. And the wonderful part is that, I'm not here to try to be able to say, oh, NervesHub is a website and come to our website and sign up for an account and, we can try to be able to get users to be able to give us money. Nerves Project and NervesHub is completely open source. And so the idea is that, yes, if you want to, you can sign up for an account at nerveshub.org. Trial accounts are available. That system is all scalable and secure. But the reality is that for enterprise users and people who like to be able to have things in-house, we anticipate and allow you to be able to just spin up your own instance of NervesHub and use it as you see fit. NervesHub is also extensible in that we can allow you to validate your device's authenticity through your own backend. So in this case, we can see if we spin up our own web server using Phoenix, we can actually allow our device to connect to our web server, and we can query NervesHub to be able to ask to make sure if that device is valid. And there's also a full REST API available to be able to use in case you have other backends like Rails, Node, whatever you might be able to be using. So it'll integrate with your existing services as well. So let's see NervesHub in action a little bit here. Here's NervesHub's panel for devices. We can see I have a Raspberry Pi Zero that's on display up here, and it's online. One great feature about NervesHub is that it gives you advanced debugging tools. For example, if you enable it, you can get a remote console directly through the website. And also, we'll see that from the NervesHub here, we have the commands like pushing available as well. So let's say I bring up the code for this, and we make our serious update, and we mix new firmware. Once we've created the firmware, then we can publish it using our private keys. This step always takes a while when you're doing video sharing. It's pretty funny. There we go. So then we'll say mix nerves under hub.firmware, and we'll do publish, and we're going to deploy it right to our test group right away. So we'll say, yep, that's the firmware we want. We'll enter in our local signing key. That signs the firmware, which is another interesting thing that I forgot to mention. All the firmware that you push into NervesHub is signed by keys that you own that we never see. So you can trust the fact that the firmware that goes in is the same firmware that comes out, and that it hasn't been tampered with in any way. And then once I do my password here, we'll see it uploads a firmware, and that my device that's online is going to start to receive an update. Oh, and failed to update deployment because that deployment probably doesn't exist. So wonderful demos keep going on. Getting started with NervesHub. You can find out more information on the site from NervesHub through GitHub. The organization is nerves-hub. And there's a README guide there that you can go through to be able to find out how to be able to start using it and setting it up for yourself and start integrating it within your project. Another thing I'd like to show is Elixir circuits. Circuits, as I mentioned, is the protocols. It's a group of protocols that you can communicate with, typically to these sensor devices. GPIO is the simplest one, and that's if I have my pins here, you can see on the Raspberry Pi, there's these pins on the top. That's essentially like wires that are exposed from the processor. These are GPIO, right? So they're just general purpose I/O. It's usually for like buttons and switches. I2C is a common one that we use for accelerometers and gyroscopes and other sensors, and SPI and UART. These don't sound like familiar phrases, but if you start saying things like USB and Ethernet, these are just the other higher protocols that also do similar things that these lower level ones would do, just with more pins and more speed. So I have a device up here called the Enviro Hat, which has some fun sensors on it, those fun sensors, we can see it's not that intimidating to be able to get up and running with them. I'm just going to SSH to my circuits demo device here. And we can see here if I go, okay, if I want to start using GPIO, this has some LEDs on them, and these LEDs are tied into pin 4. I can just go, okay, I want circuits GPIO to open up pin 4 as an output, and then I'm going to write these LEDs to go high. And so if I bring this guy up here, voila, we can see with my board, the moment that I hit this, those LEDs nice and bright, and you just set that to 0, and the LEDs can go back off. Another fun part about this is integrating with accelerometers. So here we have an accelerometer that's on this device as well, and we can get up and running with that. We'll initialize it, which you can see the code here is just sending some bytes to the accelerometer. You can find this information in the device's data sheet on what you have to send. But the interesting part about this one is the reading part. Another powerful part of Erlang and Elixir is the pattern matching, especially in destructuring binary data protocols. And normally in other languages where you have to do some silly bit shifting, you can just basically pluck out and format the code from the binary stream that you want. In this case, we're going to say X is assigned little 16, Y and Z as well. And then we can just do some quick computational math on it. And I can't stress enough how simplified this code is compared to other platforms. And so if we were to then just go in and say, let's read this accelerometer, we'll see that we get out that, sure enough, does everybody feel 1 unit of gravity happening in this room? Right? Yeah. And if I turn this a little bit on its axis, we'll see that we'll get a 1 in a different axis. And same thing if I turn it in another axis, close to -9 there, but so on and so on. All right, so since there's so much in the ecosystem to cover, we're going to get through this. The last things I want to show you is Schneck. Schneck is an OpenGL user interface library. A man named Boyd Malter wrote it, and he was basically a primary on the Xbox line. Learned a lot from his time at Xbox, especially in how to be able to hack Xboxes. And because of that experience, the user interface library that he's writing in Elixir contains a lot of the countermeasures that he's learned along the way to prevent people from being able to break into devices using user interface hacking. The important notes here is that, yes, it's accelerated in OpenGL. It's meant for 2D graphics, but it can also speed up things by being able to compile the graph of objects at compile time instead of having to structure them at runtime. It can build pretty user interfaces such as this. It has a series of primitives that it includes, like triangles and squares and lines and images, text. And you can also then use various components that are built and prepackaged based off of these elements. And it'll do a series of transformations as well. So you can move things around, scale them, and it's all smooth and rendered properly with OpenGL. And before I show you some Schneck stuff, I also want to be able to say some words about Phoenix. Phoenix is the web backend to all of this for building web applications. It's distributed, scalable. It embraces the MVC style, but it's also good for building APIs. And it's super reliable and fast because of all of the benefits that we get with Erlang and all of the speed that we get with concurrency. Phoenix also contains this very interesting extraction called channels that's included, which is essentially a pub-stub subscription mechanism where you have clients that receive to a broker, and the broker then distributes those topics to other clients. And channels allows Phoenix to be able to do some enhanced real-time things. It's almost like it was created for Internet of Things devices, and that people building website and web applications that use Phoenix channels have this ability of just reaching out and like grabbing a connection to a device. It's very easy to be able to implement. And it'll also be able to work between devices and browsers, and there's Phoenix channel libraries that also are out there for mobile devices too, so it's almost anything you can connect through this abstraction. Another interesting thing too is that we've done a load test on Phoenix in the last couple of years. We were able to, on a single node, push about 2 million device connections simultaneously, a reasonable sized payload in under 5 seconds to deliver to all of them. So it's highly scalable and highly reliable. But the nice thing about Phoenix that just came out recently is this thing called Live View. because it has this channel abstraction, Live View is doing server-side rendering without the need to be able to write JavaScript. So in this case, you can do interactive, rich user interfaces that are server-side rendered, such as you saw the thermostat example, or in this case, like auto-completions or validations without having to write additional JavaScript or anything like that. It's all under the hood using this reliable transport as well. And so let's take a look at this one. So here I have a Phoenix Live View app, the thermostat, and we can see we can just click it up and down on degrees to work together and bring this all together on saying how we can build these full IoT platforms. I also have a Scenic application that I can run here that connects to the Live View Phoenix app. And now, so here we have a simulated device that we're running on our laptop, so we can do some user interface development that just displays this. And these things synchronize to where over channels, all the messages go back and forth and everything's up to date. But to be able to take this one step further, I have a real device right here. So let's go to, I believe, this one, this one. So I have this real device right here. And this real device also is connected to the Phoenix backend, receiving all these messages. And because we're using circuits in this case, we have access to the GPIO for these buttons to be able to actually use them. So this is just like steps away from a real thermostat. Just plug some wires into the one at home. I was tempted to do it to the one in my hotel room, but I don't know. And then the nice thing here, too, is that if the Phoenix application were to crash, I think it's this one. Let's just kill the Phoenix server. We can see we can handle these gracefully. The live view is waiting for reconnection, and our device here is also waiting for reconnection. And if I bring the Phoenix server back up, then everything connects back, and the state returns back to the reconnected state, and we're in a known good working place again. So what makes it hard? Well, reliability, tooling, multi-languages, IoT, all of this stuff can be taken care of for you under one ecosystem with Elixir. I'd like to be able to showcase a few parts of how we're using Nerves in production. Nerves is not only just for building for maker stuff, but we have some top-level companies that are shipping products with it, one of which is APC is starting to be able to ship Nerves in their server-grade battery backup units, and those are in production now. We also have Latote, as I've mentioned, that I've worked for. We implement those into our warehousing to be able to create devices that allow our workers to be able to track garments using RFID. And we have an example here of SmartRent, which is a US company that's installed for smart home installations that uses Nerves on this board here to be able to do smart home automation for property rental management. And Bowery, this is a vertical farming startup in New York City that uses Nerves to be able to connect and control tons and tons of devices for indoor vertical hydroponic systems. And also another fun one is FarmBot. This is one of my favorite ones. This is a farming robot that you can control. It's basically a large CNC machine that'll plant and seed and weed and water. It uses computer vision to determine where the weeds are in your garden and just eradicates them with this tool. This is actually a picture of the one that's installed at my house, which is kind of pretty fun. And from there, if you'd like to learn more about our project, you can visit us on the Elixir forum, where you can get history, or you can come to our Slack channel and check us out in the Nerves in the Elixir Lang Slack, and check us out on the Nerves channel. And also, if you're interested in being able to start deploying and using NervesHub, please come and see us in the NervesHub channel in that one as well, and we can talk more from there. All of this is possible by community support. As I mentioned, NervesHub, and everything that we're doing with this project is completely open source. So we love it when people come in and help by doing little tiny PRs to documentations to large features and just getting involved in the systems themselves. And from there, thank you very much for having me and seeing these demos.
Thank you, Justin. This was super interesting, and I'm so glad that you're so focused on security, because with IoT, I think that's the most important thing. Before we go on to a 10-minute break, we have time for a few questions. So Julia asks, can you tell us about interesting projects that made it into production and where this stack made a difference?
Sure, yeah. One of the original adopters of Nerves was a company called Rose Point Navigation out of Seattle. And they used Nerves to be able to do high throughput CAN bus messages from all the sensors and data that's coming through on boats. And as it turns out that we found out later, those systems are installed on I think it's almost 80% of the traffic that goes up and down the Mississippi River runs Nerves, and that's for like high throughput. It really shines in that case for concurrency.
All right, thank you. Thanks for the question, Julia. Mirko is asking, coming from a C++ world, what would you list as a main advantage of functional programming over object-oriented programming?
I would say the main advantage that we've seen is that the actor model and functional programming paradigms that exist in Elixir and Erlang allowed us to be able to think about systems more as, it seems to blend itself a little bit better towards state machine usage, and it creates less spaghetti code when it comes to all the callback spaghetti that you get usually when having to implement this in other languages. Now, if you need to be able to do real-time work, then you're still going to have to dip out to C and C++, but we have lots of examples on how to be able to write what's known as a port or a NIF, which is a native interface function that can be used in conjunction with Elixir and Erlang, so that you can still do those lower-level things. And so this wouldn't necessarily be like a replacement, but it can handle a lot of the connectivity. And the idea is that if you need to be able to use lower-level languages to be able to get more real-time concerns, then let Nerves and Elixir and Erlang do what it does best, supervising those things. FarmBot, for example, uses a Raspberry Pi and an Arduino, and the Raspberry Pi handles all of the high-level communication and the uplink and all of the complicated things that if you were to have to do it in C and C++ would take you a much longer time. But it then, as that main processing node, is able to supervise the connection that it has with the Arduino, and if something were to stall out, it can, just like an internal process in Erlang, it can sort of send a power off, power on reset to that device as well.
So cool. So Pietro is asking, the Erlang VM is really lightweight, but what is the memory size footprint of an average Nerves project?
Yeah, so the an average one, I would say, in the case of getting started, is about 30 megabytes shipping, and that's still bloated. We're working on being able to get that number down. So we're looking to be able to get that even lower. In addition, we're also taking steps to be able to try to enhance our delivery mechanisms to, instead of doing full-on streaming, that we'll be able to do deltas, which will make further subsequent updates even smaller. And the memory footprint, I believe, is it's definitely in the low megabytes. It's not a lot, but it also depends on how much you're doing and holding in state, and how much message handling and processing you're doing as well.
Of course, sounds amazing. There's another question here. Does Nerve not utilize Erlang's hot code swapping?
That's a great question, and the answer is really in the sense of from the top, no. And the reason for that is because when we're shipping these devices, oftentimes the Linux kernel, let's say you need to be able to turn on an additional module to handle a device, an accessory that's now being plugged in, and at the same time then you write some Erlang and Elixir code to be able to handle that accessory. The updates ship with the full systems as well on the ABs, and so by locking those two together in step, it allows us then to be able to make sure that that module is available when you go to add your code. And you can imagine if you were to disconnect those worlds that you could get yourself into some troublesome states. However, there is work in progress to be able to try to use the hot code swapping functions of Erlang to be able to do enhanced hardware-in-the-loop debugging in development and test phases. So keep an eye out for that.
Cool. Pietro asks, because of Erlang, this opens the possibilities to have interconnected VMs in these devices talking to each other. What new possibilities do we have now because of this? Do you imagine Phoenix servers running apps in real time in embedded devices?
Yeah, this is really neat. I mean, it really breaks the boundaries down when it comes to the ideas of where computers are. Even the actor model to begin with doesn't care where a process exists. By enabling distributed Erlang, it gives you the capability of just over the WAN, even connecting devices together. And so what I would see in this case is new possibilities that we might be able to see is Phoenix servers might be able to have, pixel pushing in that case, if you were, or you might be able to even like imagine this as a way to be able to deliver an additional, like stream additional enhancements down. But the way that we've seen this before is there was a talk I gave, I think a year ago, where in the last 15 minutes of the demo, the talk, I did a demo where I built a photo booth live on stage out of parts. And what I did was I took two different computers. One was a Raspberry Pi Zero and one was a Raspberry Pi 3. And using distributed Erlang, connected those nodes together. And so locally, it really makes a lot of sense to be able to do distribution. But when you're connecting up over the WAN, it makes more sense to be able to federate those clusters instead of trying to be able to make them one giant cluster.
All right. I think we have run out of time. So thanks for these amazing questions. And please give it up for Justin Schneck.
Thank you.
And on behalf of Craft's organizers, let me present you this